Hi, I'm Juan, and I will be presenting our 16 heads really better than one. It's a paper from last year. So the transformer architecture was a big breakthrough in natural language processing thanks to its multi-header attention mechanism. Although multi-header attention leads to very good predictions, it is very costly and it was not clear what was exactly the role of having a lot of attention heads. And in this paper, the authors make the surprising observation that a large percentage of attention heads can be removed without significantly impacting performance. But what does the transformer look like? Well, it's basically a stack of encoders connected to a stack of decoders with a attention mechanism. And here we can see that inside each encoder we have an attention mechanism, and inside each encoder we can see the self-attention mechanism and the encoder-decoder attention mechanisms, which were the arrows connecting the two stacks in the previous slide. And these attention layers are basically softmax layers that allow the network to understand the relationships between pairs of words. For example, here it means the animal. And multi-head attention is the vectorized version of attention. Here we have the number of attention heads, and we will be using this masking variable to shut them down. And I think it's very natural to define the importance of a head by the expected change in the loss function after we shut it down. They basically performed two experiments. The first one was with the original transformer with 6 layers and 16 attention heads per layer in the machine translation task. And the second experiment was with BERT, which was a big breakthrough in NLP 2 years ago with 12 layers and 12 attention heads per layer. So here we can see what happens if we shut down one attention head in the model. On the left we have the results for the original transformer, and on the right we have the results for BERT. And we can see that although there are some important heads, pretty much all of them are not important. And if we change the test data set, it's actually pretty much the same story. The results cluster around the original performance. Here we can see the evolution of the performance with the pruning, and if we sort the attention heads with the change in performance, we have this green curve, and the blue curve is what happens if we sort them with the importance metric that we defined before. We can see that two things, that the importance matrix is actually better than the raw performance to select the important heads, and that we can pretty much take away between 20 and 30% of the heads and still have good performance. Turns out that the encoder and encoder part and the decoder part of the transformer are not that sensitive to pruning, but the encoder-decoder part that connect to the two stacks, it's actually very sensitive to shutting down of its heads. And we can see that if we start pruning from there, the performance decays rapidly. And how about the head importance during training? Here we can see that if the model is pruned up to 50%, it's actually stable and achieves still good performance. And the authors notice that there are like two kinds of behavior. If you start pruning in the early stages of the training, you can have a pretty much linear relationship between the pruning and the performance. But if you prune from the end of the training phases, you can find a lot of attention heads that are not that important. To conclude, the authors present a simple algorithm that greedily and iteratively prunes away attention heads that seem to be contributing less to the model, and that large parts of the network can be removed with little to no consequences, but the majority of heads must remain to avoid catastrophic drops in performance. So that's it, and thanks for listening.